Good morning, everyone. Welcome. Welcome to another Spring Showcase. Today marks Showcase 35 for Spring. We'll be hearing from United Utilities about how their innovative Loop project will demonstrate how the water industry can play an active role in the production of graphene and hydrogen from a fully sustainable source feed material. For those of you who might not know, Spring are a centre of excellence for innovation in the UK water sector. And we're here to create centralised intelligence around what already exists in the water innovation space. Our goal is therefore to enable collaboration, remove duplication, and accelerate innovation within the water sector. Before we begin, I just wanted to touch a little on why we do these deep dive knowledge sharing events like today. So globally, the water sector is under significant scrutiny at the moment, and we really need to accelerate problem solving, and knowledge sharing is one of the ways we can do that. So last year, we partnered with the Economic Regulator for England and Wales to build a view of what best practice knowledge sharing looks like. We brought together senior leaders and innovation managers to design a vision for knowledge sharing. What is it we're actually trying to achieve? And ultimately, the answer was that we want to unlock faster adoption by creating a world-class knowledge sharing culture. So from there, we built out 6 best practice principles. Number 1 is learn from what already exists before committing to innovation projects. So Spring and the presenters on this call can all share knowledge, but we want to be sure that the receivers of the knowledge have the resources and capacity required to make that change and that they feel empowered to do so. So Spring is building a centralised source for what already exists so that you can come and check in with us and learn from what is there before investment is made on new projects. Number 2 is target innovation insights to the right audience to meet our objectives. So we want to make sure the right people are listening to the lessons. So for today, do we have our programme managers on the call? Do we have our engineers? And do we have the right decision makers involved in the lessons learned? Number 3 is that insights are regularly shared through multiple channels from day one of the project. So historically, knowledge share happens at the end of a project, and we really want to start moving towards a model where we share from day one. And we want to make sure that what we're sharing is open and centralised too. So we want to make sure that we are all being open and honest when it comes to the knowledge from innovation projects, which can feel a little scary, but it's always the best way when it comes to knowledge sharing, sharing both failures and successes. We want to make sure it's all in one place too. That's why Spring are here, because fragmented knowledge is much more difficult to engage with and learn from. Number 5 is insights from innovation successes and failures are shared. So as we all know, the failures are just as important as the lessons of success, and we'll be hearing about some of those from our team today. And finally, we have number 6, people are empowered to receive and embed lessons from external sources. So Spring and the presenters on this call can all share knowledge, but we want to make sure that the receivers of the knowledge actually are able to act on that knowledge shared. In terms of what will be shared, I would encourage you to take a look at the Water Innovation Strategy 2050. For anyone who hasn't seen that document, it lives on our website and it outlines 7 main themes, with challenges sitting under those themes that we're currently trying to tackle in the sector. We also hosted a webinar about these best practice principles on the 21st of November last year. So you can watch that back on our platform if you'd like to hear more about these principles. You can find it under knowledge along with our previous showcases and case studies, and a link to that will be in the chat shortly. Back to today, I'd just like to give a warm welcome to all the audience members joining us live. We thank you for taking the time out of your day to do so. We are joined by the UK and Ireland water companies, supply chain, academia, and lots of overseas colleagues too. So welcome to the call and thank you so much for joining us. We'll be linking a poll at the end of this showcase to find out how interesting you found the information shared today and whether you're hoping to go away and take action on it afterwards. So please do submit your answers when you see that come through at the end. You'll get the chance to ask the project team any questions too throughout the event. So make sure you keep putting your queries in the chat throughout today's presentation so that we can ask the presenters at the end. So on to today's session, I'm just going to run through the agenda and introduce our speakers. So we'll start with a kind of introduction to knowledge sharing from a virtual Kira Brocklebank, followed by the context behind the Loop project. We'll then have an overview of the learnings behind enabling works and the technical details before going into a short break. After the break, we'll have a panel-style reflection discussion before wrapping up with a Q&A. Speakers wise, we'll be hearing from, again, a virtual Kieran Brocklebank. He couldn't join us today in person, unfortunately. Richard Clark, Programme Manager at United Utilities, Susie Hill, Project Manager at United Utilities, and James Cross, Head of Projects and Services at Levidian. So without further ado, I'm just going to pop off the camera and mic so we can hear from Kieran.
Hello, I'm Kieran Brocklebank. I'm the Head of Innovation here at United Utilities. We deliver water and wastewater services to 7 million customers in the northwest of England, and we're proud to do so. I'm speaking to you today about innovation, and in particular, the crossover with knowledge sharing. Why knowledge sharing is so important? Well, we believe it's crucial for a few reasons. It sets the tone for how you're going to behave, how you're going to operate. If you're a sharing organisation, then maybe you're open, the doors are open to collaboration, the collaboration that the water sector really needs. Knowledge sharing, of course, is a way for experts to get together, to pool their insights, their individual, diverse views, and help them develop more effective solutions. By sharing knowledge, sharing experiences, sharing data, sharing insights, then maybe as a sector, we can avoid making repeat mistakes. It's okay to fail if you're trying something for the first time, but you know, if you're failing on things that other people have failed, well, that's wasted effort. And you know, ultimately, knowledge sharing, great knowledge sharing, drives more innovation, and it drives the adoption of innovation. But how do we know what great knowledge sharing looks and feels like? How would you recognize it? Well, it would be helpful, wouldn't it, if there were some guidelines? And these 6 are a great start. So thinking about each of those 6 in turn, our first one's about learning from what already exists. Don't start any new ventures without really searching the market, finding out from all of your contacts, your networks, your peers, in sector and out of sector. Find out what already exists and make sure that you're not inadvertently duplicating, wasting effort. Number 2 then is all around those insights that you discover, making sure they reach the right audiences. Don't publish things in places where your target audience isn't going to read them, isn't going to watch them. Find out where your audiences are and target your sharing to those places. Of course, if you're thinking about knowledge sharing, about finding information, then go to the right audiences, go to the right places to seek out that information. And when those insights are being shared, make sure they're shared regularly. Not just once at the end of a particular venture or innovation trial, but throughout. Share learnings in small, bite-sized pieces. The Ofwat Fund newsletter is a great start and a great nod in that direction. That's a real positive movement. Some of that learning has been broken down into digestible chunks of information that really hit home. And of course, when it's shared regularly, consider different channels, different ways of sharing. In person, conferences, workshops. Maybe it's a dedicated in-person day that you've curated, that you've designed a day specifically to share information. Maybe it's online in addition. Maybe it's a showcase event like this. Maybe it's a case study that's published, for example, in the Spring website. Maybe it's some open data that can be shared with Stream. Maybe it's information that your customers want to hear, your target suppliers. What about your website? Have you updated that lately with the latest information? Of course, the knowledge needs to be open, accessible to all the right people, and of course, ideally centralized. which is why the power of spring, the power of stream, Uckwea, places like that are so vital to us in the sector. And those insights shouldn't just be celebratory successes, although having self-esteem around innovation is important. It is important to share when things go well. That really, really helps people understand what they could copy. But why not share things that didn't go so well? Make yourself a little vulnerable. Share things that didn't go well. How did you dust yourself down? How did you go back a few steps? And how did you proceed in a different fashion to be more successful next time? And finally, people are empowered, making sure that that right audience can receive the information and that they are given permission to act on that information, because the action is the most important. Sharing knowledge makes us feel good. It increases our capacity of knowledge. But of course, action, doing something with that knowledge, is the most important, vital thing. That's what gives our customers, the environment, and society the benefits that it's really looking for from innovation. Thank you.
Great, so thank you to Kieran for that lovely little video about knowledge sharing. We'll now go into some context about Loop from Richard.
Brilliant. Okay, well, thank you very much, Leah. So, hi, morning everybody. I'm Richard Clark. I'm Programme Manager for Engineering Innovation here at United Utilities. And thank you very much for joining us for our Loop Showcase. This is the first time this technology has been used in this contest, and that is the municipal wastewater treatment sector. And we're very proud of our team. We're very proud of all of the organisations that have come together to help us in the delivery of this project. And you can see some of the names of those organisations across the bottom of the first slide there. It's really important when we're delivering innovation projects, but everyone realises that we need to flex a little bit in the way we do. We need to do things. We need to change things to really help incorporate these new technologies. And every one of these different organisations, all those subject matter experts, have had to alter in some way the things that they've had to do to help us deliver the Loop process. As I say, it's the first time that this has been done, and if it's the first thing you need to take away from this session this morning is that case. It's the first time in the municipal wastewater industry that we've taken the Loop technology, which takes our biogas and the methane, more importantly, the methane within the biogas that we produce, and opens that up into its constituent parts. We collect the carbon as graphene, and we also have hydrogen as fuel. And that's the second thing that you should take away from this session this morning. This is a fully sustainable feed source. This biogas, of which here at United Utilities we produce over 70 million metres cubed per year of biogas. That figure is over 500 million metres cubed for the UK water industry over a year. It's a fully sustainable feed source. It comes from our anaerobic digestion process. In the water industry, when we talk about hydrogen and hydrogen production, we find ourselves talking about electrolysis of water a lot. We go straight to the H2O. This is not electrolysis. This is a fully sustainable biogas-fed system. So that's the second thing, a fully sustainable feed source. And then thirdly, it's the opportunities that this opens up for not just the UK water industry, not here at UU, but for other industries as well. Susie and James will speak to you later on about the detail around the Loop process and what we've had to do. But by using Loop, we're able to help decarbonise other industries across the world. The process itself, as I say, takes our biogas. Now, Levidian have used this before. They use their Loop process on natural gas, which is 99% methane concentration. We're taking a biogas that is 60% methane concentration, the remaining 40% being carbon dioxide and other elements. First time it's been done. We've designed the processor, but we're actually taking what is quite a vicious gas. It's very high in moisture content. Okay, and we've taken it from downstream of our chiller and our carbon filtration systems at Manchester Bioresources Centre. That's because that is representative of biogas that we have at other bioresources centres here at United Utilities and within the UK water industry. It's also representative of any other industries that have a biogas feed source. Remember that fully sustainable feed source. I've been with this project alongside the Department for Energy Security and Net Zero and Levidian for around 3 years now. And we started with a phase 1 project funded through DESNZ, but looked at this at lab scale. So we took a step back and we said, right, is this really achievable? Do we have a proof of concept? And fortunately we do. What we did, we took a synthetic biogas. So we took a 60% methane, 40% carbon dioxide mix at the Levidian laboratory down in Cambridge. And we ran it through their lab scale loop system. And we managed to capture carbon as a functional graphene. And that's to say it didn't require any further refinement to achieve the quality of graphene that they've been achieving, whereas Levidian have been achieving from natural gas processing. And we also showed that we were able to produce hydrogen. And this led us quite nicely into what is now our phase 2 project. So we've been working again through funding that's been provided through DESNZ. We've been able to move forward with the loop technology, upscale it to what is now a 15 meters cubed per hour system. And at Manchester, we are now processing biogas. We've produced graphene, we've produced hydrogen. So we've scaled up very nicely. This isn't the end of the story. There is more work to do. We need to get larger with the process, but the team have made very large steps towards making this all a reality and being able to say that from a fully sustainable biogas feed source, we're able to provide graphene, which can be used in products elsewhere and in other industries, helping to decarbonise those industries, and hydrogen, which we can use as a fuel for large industrial users or energy users, that is, and public transport and large-scale transportation. We've talked a lot during the delivery of the project around the commercialisation approach. Where does this get us to? And we decided that very early in phase 2 of our project to look at 4 scales. We looked at the local scale. So what does it mean here at United Utilities for us? What are the options for us? What are the possibilities for us? We looked at regional scale, so working alongside colleagues at Liverpool City Region Combined Authority and all 3 of the Liverpool universities, we've managed to bring together a good picture of how we can use the loop process to, yes, produce graphene and hydrogen, but move that forward into the marketplace, so become a supplier within a hydrogen market, for example. We've also looked at the national scale. So we've looked at the UK water industry and about 500 million metres cubed per year of biogas that's produced. And so we haven't got a complete answer, but we've got part of the answer to this very tricky puzzle of how we help to decarbonise the water industry. But we've looked further than that. So anywhere that produces biogas, the loop can be used. We've shown that the loop can be used in those situations as well. And then finally, on a global scale, this is a great opportunity. It's very big, but it's a great opportunity for us. We can move into markets such as in the Middle East, where Levidian are already working again on natural gas-based systems. But we could look at Europe, where we've got 17,000 biogas producing sites. And then finally, if we move to North America, which we know Levidian are already looking at, you've got 15,000 sites that are proposed for biogas production. So they're not existing yet, they're new sites to come on board. So it's a really, really exciting time for this technology. Massive opportunities out there. So please do listen to Susie, listen to James, what they have to say about the detail around the loop technology, the lessons that we've learned and what we've been working through as a team. But just remember, it's the first time we've done this. This is a fully sustainable route to graphene and hydrogen. It's a fully sustainable feed source. And then finally for me, the opportunities. The opportunities are immense for this technology. It's really good to see it's upscaling this system and helping not just the water industry, but much broader than that, other industries to decarbonise. Thank you very much for your time. I'll hand over to Susie.
Thanks, Richard. I'm going to move that a bit closer. Hi, so I'm Susie. I'm a project manager in the engineering innovation team working with Richard, and I've been on the project for about 2 years. Yeah, so I've sort of been part of the project since we moved into the delivery phase. I wasn't on the project while we were looking at the initial sort of feasibility stage. And I've been sort of leading on the design and delivery of the enabling work. So essentially how we're going to plumb in how we have plumbed in the loop system at MBC. So I have just put a bit of a high level journey, I guess, of the design phase on the screen, because I think I want to just talk a little bit about what we've had to do and how we've had to work collaboratively with lots of different people to make this a reality. So for the purpose of my talk, I'm going to say that Levidian handles everything inside the box and we handle everything outside the box, just because it's nice and simple. And then when I hand over to James, he'll be able to talk you through what's inside the box and how they've commissioned it. So for this whole process, we've had to work very collaboratively with Levidian, and I've tried to highlight that by putting Levidian above and then UU and other sort of disciplines below the line. So at every stage, you know, we've had to go through our hazard identification, HAZOP, access lifting and maintenance studies, drawing up our P&IDs and general arrangement diagrams. And at every stage, this has been, you know, not just as simple as we're building something and we need our P&ID drawn or we need our HAZOP completed. We've got a massively complex piece of kit inside a box, but we also need to assess how that fits in with the MBC process. So at each stage, we had to incorporate work from Levidian as well as work from United Utilities and various contractors to ensure that those documents produced were of the right standard and essentially just made sure that everything was completed in a safe and effective way. So the one I want to highlight on this is the DESNZ element. So I don't know what all your backgrounds on the call are, but if you're proposing to do anything on a gas site or anything that involves the sort of explosive atmosphere as part of DESNZ, then you will have to do a DESNZ risk assessment and make sure that you have drawings which show where the zones are, so the different explosion zones in your kit and also in all of the enabling works. And this has to integrate with the DESNZ risk assessment for the site to make sure that site understand what they're getting and how their risk assessment might change. So this was quite a complex activity because we have the DESNZ risk assessments from Levidian, as well as then having some enabling works DESNZ risk assessments. We actually completed them separately and then worked to basically bring them together and make sure that everything was covered, which is a bit of a non-standard way of working. And I think I wanted to highlight that because these sort of non-standard ways of working are quite common in innovation. We have to make things work for our project, but we have to do that within the confines of obviously the law and all of our internal sort of processes and procedures that we follow. So the UU DESNZ team and the UU mechanical team were very heavily involved in getting that DESNZ risk assessment agreed off the ground, everyone being happy with it, and that was quite a long process. But I think as I go along, I'll try and talk a bit about the wins and the successes and the opportunities that we've had. And this was one of the wins because I now feel like that team and those people understand the loop process, they understand what we're trying to do, and they're getting us and they've been helping us along the way. And then finally, in the design element, we go through well, it's kind of design install, but basically getting ready to install all of this, we have to go through our standard work authorization procedures. So this is where we bring our external contractors who are going to complete the work to site, and we have essentially a large meeting to discuss everything that's going to happen. We look at the risk assessments, method statements, and approve them to begin work. So what I'll do on the next two slides is I've got a few pictures and diagrams of what it looks like, and then I've got another slide like this, which is a bit about the installation. So on this slide, you can see the containers on site. This is quite an old photo, so actually now there's a lot more pipe work on that picture. But essentially, what you can see is the UU biogas, of which Richard said obviously there's 15 cube an hour going into the loop at one end. The loop units itself produces a hydrogen syngas. So because we've got all that other stuff in the gas, you know, the moisture, carbon monoxide, the CO2, we're not going to get a pure hydrogen gas straight off. So we get a hydrogen syngas, which then goes through container 2, which is a separator. So for the purpose of my part of the presentation, you just need to know that it's the loop unit and a separator. And then we've got the gas coming off the separator being blended, and we're sending that for the purpose of the trial back to our CHPs, because the hydrogen production is so small. It's, I mean, 15 cube an hour and about 3,000 MBC. So what we're doing is blending that. Obviously, if we take this forward and we want to use this in the future, we would then look at what would we do with that hydrogen, how would we store it, how would we transport it. But yeah, for the purpose of the trial, it's being blended and sent back to the system. And then we've got the graphene represented by the pink line, which is then taken off site. And that's being looked at by Levidian's lab in Cambridge. Right, next slide. So this is just a few pictures, and again, I'll leave it up to James to tell you a bit more about the loop unit itself. But this is just some pictures on a nice sunny day. So you can see the 2 loop units on the side and the left there. And then we've got an argon feed, which sort of formed part of the enabling works, which wasn't actually on the previous diagram. And that's in the middle picture. So the argon's used to purge the system. And instead of bringing in canisters for this, we actually ended up just bringing in a cryogenic vessel, which added a little bit to all of the risk assessments and various design elements, but ultimately was the right choice. And then in the far right picture, you've got the graphene collection node, which James will talk about again in a minute. So thinking about the pictures and the diagrams we've just seen, I've put this on screen to talk about how we installed it and how we commissioned it. So coming from the design, the containers were delivered and craned in, which was a mammoth exercise because they were quite heavy. And then we installed the enabling works, or we had a contractor install the enabling works for us. There was a testing and commissioning phase, which included a lot of different things. And going back to the DESNZ risk assessment and DESNZ elements, there was a lot of inspections of any rated equipment, so equipment that sits in zoned areas, electrical testing, strength and tightness testing. And I think what I want to point out here is that there was a lot of, I would say, collaborative work between sort of United Utilities, the contractors, and Levidian to make sure that all of this was done in the best way possible. We're working with, you know, new kit that people haven't seen before, and it was quite complicated to get through all these different steps. And I think it's just not to be underestimated when you've got so much pipe work running between 2 containers that, yeah, as Richard said, it's the first time anyone's ever done it. So naturally, it didn't quite go to plan, and it took a little bit longer than we expected it to. But I think the key thing to point out is that it's really important to have a team of people that are bought into this sort of way of working. So having contractors on board that understand that we need to be flexible with scope and that things might change. Having engineers on board who are sort of willing to look at challenges and not run away and not sort of throw the rule book at us, and work with us to understand ways of getting around those in the best way. And I think that's pretty much it from me. I'm trying to think of anything else. No, that's everything I've got down. But yeah, I'll hand over to James, because it was at this point, after we purged the lines, that we then hand everything over to Levidian to start commissioning.
Thanks, Susie. Morning, everybody. I'm James Cross, head of projects at Levidian. So I've got some slides to share the learning around loop and, as Susie said, what goes on inside the box. I'm conscious Levidian is not necessarily a well-known name in the water sector, so I'll start by giving you a bit of background on who we are and what loop is. So first and foremost, Levidian is a British climate tech company. We span out to the University of Cambridge more than a decade ago, and we've really built a company around the loop technology, with the idea that that can be used to decarbonise hard to abate sectors. So we're not going for the low hanging fruit, we're going for the difficult industrial processes. The way we do that is we use loop to deliver on the 3 pillars that we talk about a lot. So we're capturing carbon, and we're not just capturing it and burying it under the sea or wondering what we're going to do with it. We're capturing it in a form that provides high value. So that leads us on to a carbon utilisation pillar. So we take the carbon in the form of graphene, that is a high value, flexible, multi-application material that has the ability to then further decarbonise the products into which it goes. And the final point is around carbon prevention. So the carbon we capture is then not emitted to atmosphere. That also generates a hydrogen gas stream, which again provides further decarbonisation potential. But where the technology gets really interesting and what makes this such a unique project is the decarbonisation potential of Loop is directly tied to the amount of carbon inherent in the gas and power that Loop consumes. So on a site like the one we've taken here, where we have a sustainable electricity feed, a sustainable gas feed, what we're doing is producing carbon negative hydrogen, carbon negative carbon, and that's a really powerful message and a really sustainable forward-looking picture. So that's the really exciting point of the project for us. So what's inside the box, as Susie said? Fundamentally, we have a gas stream that could be natural gas from pipeline source, that could be biogas, it could be flare gas. In this case, it's a biogas feed. We then take a power source, and the primary use we make of that is into microwave generators. So we're talking a microwave that's the same frequency, the same fundamental technology that's in most people's kitchen, but on a higher power scale. What that microwave then does is if we put that through Levidian's kind of core IP, the patented nozzle, as we call it, and that separates the feed gas into its constituent parts in a plasma. There are then a number of chemical reactions that follow that, and out of that plasma and the chemical reactions, what we get is solid carbon in the form of graphene and a decarbonised gas stream that includes hydrogen. So all of the Levidian projects and solutions and customers to date are based around this fundamental IP of taking a gas stream, separating it out into its constituent parts, and coming out with a solid carbon and a decarbonised gas stream. So how's that actually been applied at the UU site? So this is the largest loop we've done to date. It actually includes 5 process chambers. So that's what we call a loop 100. There is no other loop 100 on the site. So as Richard mentioned, this is a first of a kind project. Those 5 process chambers are housed in a 40-foot container that you saw a picture of earlier. And the outputs of that, both the decarbonised gas stream and the solid carbon graphene, are then extracted into a second container where the graphene is stored for removal and transfer to lab analysis and ongoing customers. And the hydrogen is separated out into a fuel cell grade hydrogen stream and a decarbonised gas stream. In the case of UU, those are both then fed back to site and run into the power generation process. So we're creating a circular and sustainable process. But what this really shows, I think, is the modularity of the system and how it can be applied to a variety of industrial sectors. So I've mentioned graphene, and Richard and Susie both did the same, but what really is graphene? Why is it better or different than other forms of carbon capture? Graphene had a birthday recently. It was discovered in Manchester 20 years ago. So purists will say graphene is a single layer thick carbon form. So it forms a hexagonal crystal structure that's really light, it's incredibly strong, it's conductive, both electrically and thermally. It's very black, which is important for a composite and a paint sector. But actually it's more than that, it's a family of materials. So graphene oxide has similar properties that in some cases are more valuable. You also have powder form and sheet form. There's a whole range of applications. And in the same way, it's possible to get hung upon green hydrogen or other sort of decarbonisation buzzwords. What's really important for graphene is not exactly how many layers thick it is, it's what decarbonisation value does it bring, what commercial and technical value does it bring downstream. So what I think I'm trying to get across is graphene is a family of materials. The value of it is what you then do with it and how you decarbonise downstream. And crucially, that we've been able to produce this directly from biogas in a sustainable fashion. So how does Levidian graphene sit within the family of other graphene production? I won't regurgitate the entire slide, but historically graphene has been made by chemically exfoliating mined graphite. There's a whole range of challenges around that, the source of the graphite, the chemical exfoliation process. The Levidian graphene and carbon capture is fundamentally different to that. We're producing a chemical process that's repeatable and sustainable. It's still routinely quality controlled, particularly where we have first of a kind applications like this. And fundamentally, and most importantly, it's been verified as graphene by the Independent Graphene Council. So it's not just our word that you're taking for it. And why is it valuable? Why is this relevant to the wastewater sectors? I've put a number of example applications on the slide, but I'm going to talk about a couple that are particularly relevant to the wastewater sector. The first is concrete. So by introducing graphene to concrete, you're potentially introducing a very small amount of carbon material, but because of the material properties of graphene, it's very light, it's very strong. By introduction of a very small amount of graphene, you can increase the structural strength of the concrete by tens of percent, which doesn't sound like much, but tens of percent of increased strength translates to tens of percent less concrete poured, and that's a massive carbon saving that's very, very relevant to big industrial customers and the water and wastewater sectors. The second example I want to talk about is composites, and particularly things like tyres. Again, introduction of a small amount of graphene allows increased wear, reduced weight, and when that translates downstream into a reduction in replacement interval, a reduction in rolling resistance, what you start to get is a rippling effect. So it's not just decarbonising the site itself that we're demonstrating, it's decarbonising the downstream industry in terms of construction and transport that has a knock-on impact to the wastewater sector. So that's the background. What have we actually shown at sites with UU? So there's a graph on the screen. What that shows is the phase 1 lab results, so the synthetic biogas, and then a couple of different results from different trials we've done on site at NBC. What you can see there is a 50 to 60% hydrogen composition, and then a remaining syngas feed of carbon monoxide, acetylene, carbon dioxide, and methane. So what this graph is showing, it looks like a fairly simple graph, but fundamentally we're showing that we have taken biogas, a sustainable power source, and produced hydrogen and a syngas feed. So that's a valuable output gas directly from biogas at a real site in the UK. So that's a first. The other key takeaways to talk about is the gas composition is stable. So over time you see very little deviation. That's really powerful for then feeding and designing downstream processes. We're not having to design for significant variability that's unusual in a biogas site. We've seen a slight reduction from the synthetic biogas lab results to the real biogas lab results. So in the lab we captured roughly 70% by volume hydrogen. In the field we're talking between 50 and 60%. The reason for that is that there was more carbon monoxide, more carbon dioxide in the input gas stream. So what that shows is there's a direct relationship between the process in and the process out. Despite that, the process is stable. The other point I wanted to call out was water content. So we designed this loop specifically for biogas applications with much higher than typical for us water content. So a pipeline natural gas feed will have effectively no water in it. It's very, very easy to handle. Biogas system has measurable and variable water content. And actually that caused no issues for the plasma itself. So that's a really positive result. We can manage stable plasma with a relatively humid gas. What we did see though was that water was condensing inside the feeding pipework to the loop. So one of the key learning points for us going forward is where we have a biogas site, we would introduce some sort of drying or condensate trap system to reduce the amount of pipework and reduce the maintenance. So it sounds trivial, but it's that sort of thing that makes a big operational difference in terms of the uptime of the loop. And again, laboured the graphene point, but what did we learn about graphene? So we have captured carbon, we have taken that to labs. What we've done is we've proven that that is a carbon stream. We've proven that that is one of the families of graphene. So it's not the same as our conventional natural gas graphene, it's subtly different. And one of the things we're going to do with the remaining trial time that we have is vary the process parameters and really explore the potential of where in that family of graphene we can take the biogas resource. Because as I said, it's not about aiming for a particular threshold of graphene, it's about understanding what's the value stream, what can we do with the graphene that allows ongoing decarbonisation and commercial value. So I'm afraid results to come on that in terms of the exact yield versus different bits of the graphene family that we can achieve. So what did we learn outside of the gas composition? This is the first time Loop's been deployed. It's the first time on a wastewater site. It's the first time it's been deployed against a biogas feed. It's the first Loop 100 we've ever done. There's a huge number of firsts. Some headings on the slide, but I want to talk about a few in particular. So stakeholder management and health and safety. United Utilities are rightly hugely safety conscious, and what this project has done is it's really introduced Loop to a whole new set of safety processes, a new set of requirements, and a new set of stakeholders. And I think it's fair to say that the technology has stood up well to that. We've been able to satisfy all of those requirements, but there was a huge amount of upfront work, both on the Levidian side and on the United Utilities side, to ensure that we ticked all the boxes, all the studies were in the right place, that the site team really understood what Loop is, because it is very different to anything else that's on that site. I would say, whilst we expect that to reduce over time as the familiarity and the technology matures, I don't expect that to change radically in deployments 2, 3, 4, 5. So I think in deploying Loop, what we would make sure we would be doing is anticipating that process coming up again and again, because it's really critical that the site teams and the health and safety teams understand what's coming, to ensure that when you seek permission to switch on, you don't suddenly discover a pilot process that you weren't anticipating. The next one I want to talk about is around the modularity of the system. So I showed that what's inside the box is 5 process chambers. That was matched to a particular size and a particular volume of gas. That modularity is really powerful and I think proved itself really effective as a way of deploying Loop. What it also did that was maybe slightly less expected was it introduced a bit more complexity on the site integration side. So there was more piping, there was more design work, there was more engagement with third-party contractors. So I think there's some work to do on the Levidian side around how do we ensure that the modularity doesn't scale and just deploy complexity on site. So how do we reduce interconnecting pipe work between the different sections of the system, things like that. The primary way we do that is we scale the system up. So our Gen 2 nozzles will achieve a similar output to the Loop 100 in a single process chamber. So that's a huge step forward. But then obviously we want to deploy multiples of those to match higher and higher outputs. And the way we need to do that is that we keep the system simple, we keep everything on the modules, so we're not duplicating complexity. New feedstocks, I mentioned wet and humid gas. The other new point for us around this site is the potential for hydrogen sulfide in the gas stream. That's a common and inevitable part of the biogas process, so it's not something that could be designed out. We were able to design the Loop to tolerate the level of H2S expected at the United Utilities site. So we're able to show that from the results of this trial, we could tolerate sort of feeds of H2S up to 50 parts per million. And crucially, we're able to tolerate that and see no deviation in the plasma. So the fundamental Loop process is really tolerant of that level of H2S. So that's a really positive point. And the final point I want to talk about is regulatory complexity. And this is really just to reinforce Susie's message. There's a lot around DESNZ, pressurized gas, even things like hot surfaces and electrical connections that the Loop touches on. So there's a real need when deploying this technology to learn the lessons of this trial and make sure that the regulatory complexity is anticipated and managed upfront in the project, because obviously the further down the project you go, the closer you are to site deployment, the harder it gets to react on your requirements. So that is all I have. Thank you for your attention. I think just to reinforce the key points, we've successfully deployed Loop, we've successfully produced graphene and a decarbonised hydrogen stream in a sustainable way for the first time on a biogas site. So we're really proud of the project that we've delivered with our partners. Look forward to any questions, and thank you very much. I'll hand back to Nick.
Thank you so much, James, and thank you to the speakers so far for their excellent presentation and lessons learned so far. We are just going to go to a break, a 15-minute break. So the time is now 10:46, so we'll be coming back at 11:01. You don't need to leave the call or anything like that. All of your cameras and mics are off, so you can just go and do your thing. You don't need to leave the call. And while we are waiting for the call to start again, we do just have some upcoming showcases that are just here on this slide for you. All you need to do is scan them with your phone camera, and it'll take you to the sign up page and more information. So if you're enjoying today's event, please do make sure to sign up to our upcoming showcases. Thanks everyone. We'll see you at 11:01. Hi everyone, welcome back. We hope you enjoyed the break. We are just now going to go into hearing about some final reflections about the project from the team. So welcome back everyone.
You're
Okay.
starting.
I'll start, that's fine. Yeah, so, well, once again, thank you very much for joining us this morning. Hope you've enjoyed what you've seen. It's been a very complicated project. You know, sometimes we start these projects, anybody that's been involved in delivering innovation schemes before will understand what I'm saying. It's, you know, it looks an easy thing to do. What is it? A couple of white boxes on a site. Comes across as being very, very easy, very straightforward. It really never is. It really isn't. There's lots and lots of moving things, and you'll notice from my presentation earlier all of the different people that have been involved in helping us to deliver the project has been absolutely fantastic. So thank you very much to them. The levels of collaboration have been really, really good. Just for people that have been willing to flex and just help us, even if it's just adjusting timescales within their current programme. I can think of just one the other day where it was Utile that were coming onto site to do some pressure testing for us. We were just able to just flex their normal working programme for us and everything they were doing just to come on site to help us because they realised that we really wanted to get back to operation. So just thank you very much for everybody that's been involved, and that's the key reflection for me, is the levels of collaboration really, really worked in our favour. Don't know, Susie,
Yeah. I was going to build on that actually and do a bit of a plug for the MBC operations team, because I don't think we would be running biogas through this unit if they hadn't been so helpful. And I think one of the learnings and knowledge that we can pass on is, if you're trying to implement something like this for the first time, that operations relationship is so important, and especially on a site, you know, MBC is a coma site. It's a really, really highly regulated, massive biogas site, and getting work through on that site is very difficult. There's a lot of processes you have to follow, and having the operational support to be able to undertake those processes and make sure that everyone's safe and that the unit is sort of delivered, plumbed in, installed, commissioned, everything safely. Yeah, that support was absolutely golden. So just make sure that you make sure you build those relationships and maintain those relationships if you look at doing a project like this in the future.
And I think just to build on that, with it being a first of a kind project, you are likely to do more maintenance, more checks and inspections, and things as simple as turning the system off and isolating it. If you don't have the site cooperation, it can take a day to get an isolation removed, and you lose a day of your trial time. So as a small company, we're very used to kind of working in an agile way, and we've learned this, so we want to do that. And that's only possible on a real world site with a very disciplined operations team, if you have that flexibility and that way of working that allows you to go through the right processes, make sure you're working safely, but also be responsive. So I think there is a potential culture clash between sort of innovative SME who is very used to sort of iterating and working quickly against the big company approach. And I think, yeah, as Susie says, that's only possible if the operations team are really engaged and bought in.
Absolutely. So no, that's great. I also feel, just kind of moving out of the kind of science and engineering space for a second, from the opportunities that are out there for this technology. There's a hell of a good positive buzz about this technology now. Now we've made that nice big step forward onto a site. We've seen what it can do. You do feel there's a lot of positive energy there around the loop process, but also those products about graphene and hydrogen. I remember going back last summer, we had a really good workshop with which Liverpool John Moss helped arrange. It was with Liverpool City Region Combined Authority, Net Zero Northwest, and Liverpool Hope University and the University of Liverpool. We were all in that room there, and just discussing what the opportunity is, particularly around hydrogen, and the positivity that we got from that. Those signals of, if we could get this loop system to work properly with that fully sustainable biogas feedstock, then the opportunities open out across the Liverpool region for the supply of hydrogen, but also that would be very common across other regions within the UK and overseas as well. So it's just lots and lots of positivity around this whole process. I'm not sure, is that something you see elsewhere, James, as well?
Yeah, the enthusiasm for the technology, I think, is great, and having worked in decarbonisation and new energy for the entirety of my career, I think it's really refreshing to work on a technology where there is a commercial case, and you can work with customers and say, well, this is how it works, and there's an investment case, and you're not trying to fudge anything or to put too much credit on just the decarbonisation, although that's clearly what you're aiming for. You need to make the commercial case. And I think the other point that to build on there is the focus on the Liverpool City region is brilliant, because we're producing hydrogen and graphene, and the cost of transporting those can be really prohibitive. So the regional focus of this technology is vital, because ideally what you don't want to do is do all this sustainable production of decarbonisable materials, or materials that help decarbonise, and then start to nibble away at that by driving them across the country or shipping them across the world. So the regional aspect is something that I think is often overlooked, and I think that's a really important point.
And Susie, you presented at the Biosolids conference. So how did you feel about how you were received there? That was back in November last year.
Yeah, I think a lot of people were quite interested to come and listen to the presentation. I had quite a few people that may or may not be on this call, I don't know, come and chat to me afterwards about it. And yeah, we've definitely said we'll be back, hopefully in November this year, to disseminate the results that we get once we finish the operational period. But yeah, it was quite refreshing to go there, because we really were the only ones there doing something like this. So yeah, I think it was very well received.
Fantastic. Yeah, I think there we can move on to some questions. Don't mind.
Great, thank you all. So we'll now go into the Q&A portion. We've already had some great questions in the chat, but if you do have any more that you think of, please feel free to keep popping them in the chat, and we'll try and get round to them. So first question from Estefani is, how long did it take from the design and handover to Levidian? And I think that's one for you, Susie.
Also, yeah, so the project started in May 2023. So it's been quite a long ranging sort of design period that we've had. And obviously, while we've been at UU designing all the enabling works, Levidian have been in Cambridge designing and building their Loop 100 unit. So essentially, we sort of came together, I think it was June last year, when the units got delivered to site and got craned in. And so since then, we've been obviously installing all of the enabling works, and it's been quite an iterative process working with Levidian, because there were some elements of build and commission that weren't quite finished, that had to be finished on site. And there were still some elements of design that came, that come with that uncertainty of, when the containers land on site, we didn't know the precise distances of all these pipelines because it's a new piece of kit we're sort of working with. So we had to work very collaboratively with the contractors and with Levidian to make sure that everything was done in exactly the right way, basically. So yeah, from sort of May 2023 till about June 2024 was the, I'd say, long extended design and build period of the Loop 100, and then we were able to hand it across.
Great, thank you. James, the next one is for you from Kirsty, who wants to know, can graphene be used in tarmac? Is there the possibility of collaborating with local councils for when they are resurfacing roads? Local council plans have a carbon net zero goal too.
Yeah, I think it's a great question. So the simple answer is yes. We've actually done a little bit of tarmac laying at our office in Cambridge just to prove that point. The more nuanced answer is that production of tarmac is a really good example of a very large scale material. So whilst collaboration with the local councils is really important, you need a collaboration through the supply chain. So the supplier of the tarmac and the supplier of their input ingredients are also key participants to make that sort of a project work. But fundamentally, yes, we have used graphene in tarmac to reduce the carbon intensity.
Fabulous, thank you. Anybody have any thoughts they wanted to add to that? Or
I think that's brilliant.
Perfect. Richard, one for you from Owen. Is there confidence that this technology will be financially viable? And if so, do you envisage installations at biogas sites in the future?
Oh, brilliant. Yeah, okay. Morning, Owen. Thank you very much for that. Yes, so it's certainly looking that way. It's looking into the positive side of being commercially viable. It's an ongoing piece of work, Owen. So we've got Asa, and Big Asa is actually on call. He's helping us from our commercial team in UU, making sure that we absolutely know what the commercial viability is for us. What I would say is we're looking at some higher value markets for the graphene and for the hydrogen. Currently, we use our biogas through our combined heat and power engines at our sites. The loop system is providing us and others opportunity to move into those higher value market streams that James took us through earlier, whether that's our automotive based, whether that's looking at concrete, of which we pour a lot of concrete. We've got a wonderfully exciting opportunity within the water industry now, heading into AMP8, to do a lot more to help our customers and the environment. And then certainly the use of graphene within concrete can help us make steps towards that as well. As for use on other biogas sites, absolutely something at UU that we've started looking into to understand what the business case is for looking at our other biogas sites. And don't forget that this technology isn't about just the water industry. It can be used on biogas generating sites outside of our industry as well, and can help other industries to decarbonise. So certainly looking very, very positive for the commercial case there.
Great, thank you. So lots of opportunity for cross-sector collaboration as well, not just within the sector.
Yes.
Great, thank you, Richard. Okay, one from Ashley, coming back to you, James. They've said, apologies if I missed this in the presentation itself, but can you give a rough guide as to how energy intensive the trial was? What is the electrical power consumption compared to yield of hydrogen and graphene? And how do you anticipate this to change with scale? Thank you.
Thanks, Ashley. It's the nub of the question, right? It's exactly what the trial should be showing. So electrical power consumption was actually lower than we anticipated. So we're consuming roughly 35 kilowatts of power when the loop's running at full output. That's processing 15 meters cubed of input gas, and roughly half of that by volumes coming out in the form of hydrogen, and the graphene yield, we're talking somewhere sort of around a kilo an hour roughly, but that's quite variable depending on the process conditions. The important point to bear in mind with the energy balance is that the output gas is within a few percent of the calorific value of the input gas. So what we're not doing is destroying the energy balance of the input gas, which is really important if you're then using it in a combustion process downstream. So yeah, I hope that answers the question. It's obviously we could spend hours and go into lots of spreadsheets around the energy consumption, but at a high level, those are the numbers.
Great, thank you. So we've had a few more come in, so I'll throw this open to the speakers who wants to answer. One from Andrew is, what is the fate of the oxygen elements when carbon from CO2 is turned into graphene? I assume O2 isn't produced?
Yeah, I can take that. So you're right, O2 is not produced. It's O2 is very reactive. So what happens is that reforms with some of the carbon, and that's what creates the carbon monoxide and carbon dioxide outputs that I showed on the graph earlier. So inside the plasma, yes, those oxygen atoms will be separated out, but they very quickly recombine. So what we see on the output gas is that more syngas production, which is in itself quite interesting because syngas is a valuable commodity in its own right.
Absolutely. Good.
Great, thank you, James. Does anybody else have any thoughts they wanted to add to that? Or
Not
James's question, I can see the next one.
perfect. Okay, so James, back to you. From Hannah, who wants to know, in terms of biogas as a feed, how good are the yields of H2 and C, and for C, the quality in comparison to pure CH4, not Cs?
Yeah. So I think, Hannah, thank you for the question. You're right to call out the distinction of the two feeds. So the hydrogen yield, so roughly 50% by volume is what's coming out. Whether that's good or bad, I think is tricky to answer. It's consistent with other loops and consistent with the expectations of the project. It does vary, and what we've seen from the trial results is the amount of CO2 in the input gas is what really affects that yield. So lower carbon dioxide biogas produces more hydrogen output, which in some respects makes sense. There's more hydrogen there on the input side. Yield of carbon, as I said, we're roughly in line with expectations, sort of a kilo-ish per hour. In terms of the quality, we are relatively consistent with pure CH4, but the next few weeks we're going to be trying some different operational parameters just to see where in that family of graphene we get, because whilst impurity is probably the most important form of quality on carbon, if it's graphene oxide or if it changes the crystalline structure, then that potentially reduces the downstream processing steps. So we want to really make sure we understand that. So I think I'll have to come back to you on that once we've got a few more results.
Cool. So very, very much still in the experimental phases of that one then. Yeah, cool. Great. Thank you, James. Next one, potentially for you again. I'm not sure. Okay. We'll give Susie a chance. So why is H2 rich gas separated and then put together in a stream with waste gas at the end? R&D purpose?
Well, I'll answer and then James, you can correct me if I'm wrong. But, so for the trial, we've got such a small amount of biogas being produced in comparison to what we have at MBC. So I think I said in my part of the presentation that it's 15 cube an hour in about 3,000 cube an hour at MBC. So we looked at originally, could we store it, could we use it? But the complexity that would add to this trial was huge. So what we've done is we're splitting it using the hydrogen separator to prove that we can produce a fuel grade hydrogen, correct?
Correct.
Yep. And then once we've sampled that and made sure that we can in fact produce that as part of the trial, then we're just blending it and sending it back to the process. And it's important to note that we're currently sending it downstream of our gas to grid takeoff point, because there's a very, very finite amount of hydrogen that you're allowed to have in your gas to grid stream. And we wouldn't exceed it, but we were quite close. So yeah, that's why it's being sent all the way down the way, basically.
Can I add one thing?
Yeah.
I think the other aspect of this is it's a coma site, so the quantity of gas stored on site is a very important topic in terms of the regulatory oversight at NBC. So whilst what we were primarily trying to do is demonstrate that we could produce fuel cell grade hydrogen and understand the operational parameters of that, what we weren't trying to do was expend a lot of the project's resources on modifying the coma permissions for the site and all that stuff that you already know how to do and doesn't really contribute to the core learning of the project.
Is there a potential for that to become a separate project in itself, the kind of storing element and
storage and transport? Okay, are key things, and that's what came off our work with Liverpool City Region back in the workshop that we did with them. there's people out there that want to use the hydrogen. There's industries that want to take on hydrogen as their main fuel source. Okay, there's industries that want to take on graphene also. But just focusing on the hydrogen bit, that is an area where everybody, I think, agrees we need to understand how to transport it. You know, it's all very well if you have a pipeline available just there to inject the hydrogen into, but not everyone's got that.
Yeah.
So we need to look for road transport. How do we safely get hydrogen distributed out to different industries so that they can use it? So it is a part of the ongoing hydrogen puzzle.
Okay, great. Thank you, Richard, and thanks to Susie and James too. Another audience question from Callum is, can the process be optimised to react to market conditions, i.e. if hydrogen or graphene prices change, can the technology be operated to focus on the production of one product over the other?
Yeah, so we typically operate the loop under very similar process conditions, regardless of the application, and the reason we do that is because we've got several years of operating the loop in that way, so we understand the maintenance, we understand the performance, we're very comfortable offering kind of guarantees and contractual confidence to our customers that particular outputs can be achieved. That said, we are very aware that there are a number of parameters we can adjust in terms of flow of gas through the system, amount of power that translates into microwave energy, and we know that when we adjust that, we can either capture more carbon or push more hydrogen out of the system. So there's a trade-off around electrical efficiency per unit of hydrogen and carbon, total gas flow through the system, maintenance impact of those adjustments. So I think the answer is yes, within reason, but there's quite a lot of background work to do to really understand what the process conditions that we're trying to adapt to are and how that then translates into, I guess, the commercial viability of the project and what the customer will actually see over a sort of longer term duration.
And is that something that will be explored in the next steps of the Loop project, or?
Yeah, so the learning that comes out of this trial is really critical for that, because it's unusual to have variable gas composition and see different amounts of CO2. So that's something that's essentially impossible to reproduce in the lab with any level of efficiency. So what happens with different gas blends, what happens with different flows, that this trial gives us a really good sort of picture of that. And that then allows us, I think, to explore that more with particular customers. I think the other aspect is just the reality of what R&D means in terms of cost and time. So in order to do that exploration, I think you need to be quite confident that the application is not niche, it's quite broad and representative of a good industry sector.
Great, thank you, James. Does anybody have any thoughts they wanted to add to that? Or
no, it just comes back to that commercialisation piece for me. So everything that we've learned in this project feeds into that and helps us understand, like James says, what the future markets could be. How can we vary things to achieve those market outputs? So yeah, it's the first time we've done this.
Great,
it's all the building blocks of where we could go to, and that's what makes it such an exciting time for the loop process and what we're doing within the water industry as well.
Absolutely, cool. Thank you, Richard, and thank you, James. Next question from the audience, again from Hannah's, is as biogas is carbon neutral, is using biogas as feed gas really contributing to the decarbonisation?
Shall I take that?
If you want, yeah.
So I think the simple answer is yes. If you what you're doing is comparing the site or the industry with Loop with what was going before. So what's already there is a carbon neutral gas that's being either processed and fed into the natural gas network, which is an improvement over natural gas from sort of hydrocarbon sources, or being burned to produce heat and power and producing carbon neutral heat and power. If you then introduce Loop and capture some of that carbon, then that solid carbon is not being emitted to atmosphere. So you have a carbon neutral gas, a little bit of carbon reduction, and then the combustion. So the overall process becomes carbon negative. So in a way, the carbon intensity of the gas going into the process isn't the most important point. It's the delta between what you start at and what you end at. So actually the carbon intensity of the power is, I think, more important than the carbon intensity of the gas. But yeah, it's a really important point. The other one to bear in mind is what the graphene does, and actually that's a bigger carbon impact than the standalone impact on site. So if you can reduce the carbon intensity of a concrete production process by 10%, that number absolutely dwarfs what's going on site. So you have almost a scope 3 emission saving that the graphene enables. So it's again, there's a lot of nuance to that picture, and it's very site specific, but I think the answer is yes.
Yeah,
I would agree.
You haven't mentioned beyond the additional benefits of the future marketplace. I was going to put it there.
Great. Thank you, James. Anybody else want to say anything else on that? Or
James covered that quite well.
yeah,
Well,
perfect.
well,
Great, thank you. So some questions that came in beforehand are. Sorry, I'm just getting them covered up. So one for you, Richard. Do you see this as being a silver bullet answer to biogas recovery?
Right, absolutely not. Okay, this isn't the ultimate answer. This is just one of the solutions that's available to us for use of biogas. It's not necessarily, it's how we're going about using the biogas. Okay. So yeah, it's straightforward, that one for me. It's an absolute no. It's part of what we can do going forward. Okay, it's just part of the puzzle.
Makes sense.
And I just build on that and just I guess endorse it. Whilst I'm obviously very excited about Loop and very positive about its impact, I don't think there's a silver bullet anywhere in this industry. What is obvious does it provides a way of decarbonising that builds on the picture. Hopefully what it does is provide a way of decarbonising some sectors that don't have alternative obvious options. So it's hopefully it's a step in the right direction in an otherwise quite difficult picture.
You're right. We need more and more of these opportunities, different opportunities, so we can vary what we do and shape the way forward to what we need to achieve. Okay, so that's what it's all about. So yeah, if there are other options out there, please do let us know so that we can look at those as well and start shaping how we can use our biogas in a better, in a more sustainable way for everybody.
Absolutely. And is there opportunity as the project grows and goes into its next steps for other companies to get involved, both out of sector and in sector?
Yeah, absolutely. That's definitely something that we're looking at. So what is we've been doing phase 2?
Yeah.
What is phase 3?
Yeah.
Okay. What does phase 3 look like? I think we're in agreement. We need to upscale the Loop again. I think that's the next step forward is to move from our Loop 100 up to a Loop 1000. Okay, and really kind of up the scale because we need to increase the throughput based on those biogas figures that I mentioned earlier. We do need to upscale it. How we finance that's an open question. That's not. We have not got the answer to that just yet. But we certainly need to look at where we go to next.
Great. Fabulous, thank you. So next one, again for you, Richard. What other opportunities will Loop open up in the water industry? You might have touched on this briefly, but...
No, this is a great question. So it's an enabler for us within wastewater treatment. Okay, so moving away from anaerobic digestion, when we look at anaerobic wastewater treatment, so this is something that we're very excited about within the water industry and within innovation. We actually have it's an Ofwat Innovation Fund project being led by Thames Water that's looking at anaerobic wastewater treatment. Please do make that distinction: wastewater treatment, not digestion. And then if we can get to anaerobic wastewater treatment, we will have a biogas there, quite often on sites where we don't have existing biogas infrastructure. So the Loop provides us a way of using that biogas and therefore using a smaller footprint wastewater treatment technology. So it really does start opening up opportunities just within our general wastewater processing as well.
Great, thank you, Richard. I just want to do a call out before I go to the final question that we've got. If anybody does have any other questions, please put them in the chat now as we're moving on to the final question. So if we don't receive any more, we'll close up after that. So if you do have any, just make sure to put them in the chat now. Great, so final question for James is, what are the next steps for innovation at Levidian?
Yeah, there's a huge amount of potential. So our biggest challenge is picking the right ones to go at. So we have a number of projects trying to understand how Loop works in reality with real customers in different sectors. So we've talked a lot about wastewater today, but we're doing similar things with flare gas in oil and gas, with industrial boiler consumption of normal natural gas. So that will give us a wide base of understanding how Loop deploys into different operational environments, whether that's geographically or different types of industrial customer. So that's the width, the kind of forward march, as Richard mentioned. We need to scale up if we're going to have really meaningful impact on decarbonisation. We need to be processing way more gas. Part of that is deploying more loops, and what we've seen with this demonstration is we can go from a single process chamber, so that would be a loop 20, up to 5 process chambers in a loop 100. So that's a 5x increase, which is a good start. Where we go next, and we launched this relatively recently, is our next generation nozzle. So that's processing maybe 20% more than what we've done for this site, but in a single process chamber. So what that means is, rather than deploying huge banks of 40-foot containers, we made the system smaller and crucially more efficient. So by going to that scale, we get more graphene and more hydrogen per unit of power input, which is the most important factor for decarbonisation and commercial. So that's our primary focus this year, is that what we call Gen 2 nozzle. So showing that can work firstly at our site in Cambridge. So the first one of those is built and is being tested, and then that we get that out to real customers and prove it in the real world, and then we'll go again.
Great, cool. And this might be a silly question, but just from my own curiosity, is there a potential for, we did a showcase last year on infrastructure, is there a potential for that to almost aid in this? And like you mentioned, nozzles and things like that, is there an element of could the plastic 3D printing be brought into to be producing those modules?
Well, there's that obviously the other way around as well. So how do you take the graphene into 3D concrete printing and 3D plastic printing, which is certainly something we've been discussing with Changemaker 3D, who help us with the 3D printing, and Manchester Metropolitan University on the 3D plastic printing side as well. So it's the other way around for us. It's wow. It's potential for graphene use within the printing, the different printing circles that we're working.
Great, thank you. And can I assume that having the graphene being placed into kind of the concrete would make it like a more resilient concrete? Is that right?
It's a strength.
Strengthening, yeah.
What James was explaining earlier, there's an opportunity to reduce the amount of concrete we use.
Oh, amazing!
By adding graphene rather than using, well, you'd be able to reduce the amount of concrete, yes, but reduce the amount of the reinforcement part as well within that.
Great.
So we are, that's another area, obviously, that the water industry very, very interested in, because we do use a lot of the grey stuff. Okay, and we've got, as I mentioned, a very, very exciting programme ahead, but where we do have to build a lot. Okay, so to serve our customers and get the correct environmental sustainable approach to the delivery of that programme as well, and hopefully this can form part of it.
Great, thank you, Richard. So we've had just a couple more coming from the audience. So one from Alistair is the loop process and graphene products suitable for carbon credits in the voluntary market?
Yep, I can take that. So conscious there's an awful lot of noise about the value and methodologies in the voluntary carbon market. So setting that to one side, but not forgetting it, the loop process is demonstrable. It's been independently verified in terms of its carbon intensity, so that would support claims in the carbon credit voluntary market. It's not something we've done to date, so I can't tell you yes, an example.
Absolutely.
The other factor that's important is it's obviously hugely dependent on the carbon intensity of the electricity input. So again, there's a kind of worms around verification of the carbon intensity unless you're generating the electricity on site, as in this case, which is great here. It's relatively unusual.
Yes, absolutely.
So without wanting to give you too vague an answer, yes, in principle, we've had sort of certificates from DNV in terms of the carbon intensity of the process, but the reality of the voluntary carbon credits market and the verification of green electricity means it's something there's quite a lot to it.
Great. Thank you, James. Does anybody else have any thoughts to add to that one at all?
Oh, I think he does great. Well, that's really
Yeah,
nice
yeah, he
questions.
does, doesn't he? Yeah, absolutely.
Thank you.
Great. Okay, so I think that brings us to the end of the Q&A. If you do have any more questions for our presenters, I think you said before the showcase that you're happy for people to reach out to you. Is that the case?
Yeah, absolutely. If
Double
there are
check,
any
yeah.
more questions out there, just let us know. We'll do our
Great.
best to answer them. Yeah.
Absolutely.
It's yeah, as I said before, it's the first time we've done this, so there may be some things that we can't answer for you. But let's let's have your questions. We'll see what we can do.
Absolutely. I think my colleague will be putting your contact details in the chat if that's okay with everybody. So anybody that does have any further questions, feel free to reach out to the presenters. So I just wanted to say thank you to the presenters for a fantastic presentation today, for sharing the learnings so openly and honestly about this project. It's always really, really great to have that in one of these sessions. So thank you, and thank you for the hard work that went into the presentation. Thank you again to the audience for taking the time out of your day to come. We really appreciate it. And just to reiterate that the recording will be available on our platform within sort of the next week or two, along with the written case study for the project and any kind of unanswered questions that crop up after this as well. We'll also have the event slide deck on there. So anybody who wants to view that, we will be doing a LinkedIn post when that's available on our platform. So make sure to give us a follow and you'll see when that's available straight away. We've got a poll in the chat, so please do let us know, again, as I said at the beginning, how you found today and how likely you are to take action on the knowledge shared today. It really helps us kind of shape these future events, and it helps the presenters know that the knowledge they're putting out there is being used as well. So please do let us know. I think that's everything. So thank you very much, everyone, and yeah, goodbye.
Take care. Thank you, everybody.
Thank you.